Så klokken 10.
God morgen eller god formiddag alle sammen. Klokken er 10, og jeg vil godt byde velkommen til dette webinar, som vi har valgt at kalde Sikker kabelbefæstigelse med en fokus på banebranchen. Mit navn er Peter Heine Nielsen, og jeg er divisionschef i Wexøe for den her Power Division. Det kommer lidt ind på, hvem vi er. Vi har valgt at lave det her webinar sammen med vores engelske partner Ellis, og vi har i dag et par talere med. Vi har inviteret Phil Goddard med, som kommer fra Ellis i England, som er Technical Development Manager eller udviklingschef ved Ellis. Han kommer til at køre det meste af præsentationen. Og med mig her i Værløse har jeg også Henning Krammer, som mange af jer sikkert kender. Han er vores salgschef på baneapplikationer og har mange års erfaring inden for både de ting, som Wexøe har med at gøre, eller det tidligere Corrosion, men også baneapplikationer og banen i sig selv. Og så jeg selv, som står for introduktionen her af webinaret. Lige kort fortalt, hvem vi er, Wexøe og specielt Power Divisionen. Det synes jeg lige, jeg vil bruge et par ord på, fordi der er sket et par ændringer siden her foråret. Indtil februar var vi faktisk et selvstændigt firma, der hed Corrosion. Det var dog i en 5-6 år tidligere overtaget af Wexøe, men i februar fusionerede vi ind som en del af Wexøe og er en fuldt integreret del, som betyder, at alle de forpligtelser og alle de projekter og alt det, vi lavede i Skorbragi, det er kørt direkte over i Wexøe. Så det betyder egentlig, at det er de samme mennesker og samme produkter, løsninger og repræsentationer, vi har, men dog under et nyt navn, Wexøe. Corrosion og Wexøe for den sags skyld også har de her 50-60 år på banen, så vi har været ret lang tid inden for den her industri. Vi er som sagt en del af Wexøe, vi er i dag omkring 80 medarbejdere. Henning og jeg, vi sidder i hovedkontoret her i Værløse, de er 25 km lidt nord for København. Som I kan se, så holder demobussen lige udenfor, den kender nogle af jer måske. Og her på matriklen har vi også et 3000 kvadratmeter stort lager, og også en workshop, hvor vi har mulighed for at lave nogle kundetilpassede løsninger. Vi har også et regionalt kontor i Vejle. Der sidder der også et par folk fra Power Divisionen, og selvfølgelig også fra andre dele af Wexøe. Vi laver hovedparten af forretningen i Wexøe Power. Det er stadigvæk mod elforsyning eller inden for energisektoren. Banen er et segment, som vi har arbejdet også i de 50 år med, og alt efter hvor store projekter der er inden for banesegmentet, så er det et sted mellem 20-25% af vores forretning. Vi adresserer også industrien, og det er vindmøllebranchen meget, vi har gang i selvfølgelig, kunne man sige, som er en 20-25% også, og så agerer vi direkte mod nogle større entreprenører og installatører, og også sælger lidt igennem grossister. Vi repræsenterer en række premium brands, kvalitetsbrands, mange af dem med hovedsæde her i Europa. Og i dag, som sagt, så har vi lavet webinaret sammen med Ellis fra UK, som er en relativt ny partner, vi har arbejdet sammen med i en 3 år nu, og har haft rigtig god succes inden for vindmøllebranchen. Og noget af det, de laver, de har stærkt fokus på, det er netop deres applikation inden for banen, som vi synes, vi vil fortælle noget om her i dag. Vi er så fusioneret ind i Wexøe som en division, og lige for at knytte et ord på de andre divisioner, så er Wexøe nok mest kendt for deres kabelkanaler og lampeudtag og så videre inden for installationsbranchen, og leverer altså stadigvæk alt inden for det. Så er der et andet ben, der hedder Solutions, og de leverer infrastruktur til datacentre, alt inden for køling og fiberoptiske net. Og så har vi et fjerde ben, Industry, som er en industriel automationsenhed, og også komplementære løsninger inden for PLC-udstyr. Og hvor der repræsenterer vi Rockwell Automation i Danmark, og faktisk også Sverige. Så det er de 4 ben, vi har at stå på. Og som sagt, score BIM case er nu så power. Så lige ganske kort omkring Ellis. Ellis, det er en engelsk kabelbefæstigelsesproducent, og de laver løsninger helt specifikt også udviklet til banen. Og det man har stor fokus på i deres applikationer, det er at sikre de her installationer mod de stærke kortslutningsstrømme, der måtte være både inden for banen og inden for elforsyningen. Og det er alt sammen testet ifølge IEC 61914. Ellis har lavet rigtig mange ting rundt omkring i hele verden. De handler igennem distributører udelukkende, og derfor har vi ikke sådan lige umiddelbart her en komplet referenceliste, men bare i England alene er det sammen med Network Rail, London Underground, Italian Railways, Railcorp og Express Rail i Hongkong, hvor de har lavet nogle af de større ting. Det er et privatejet selskab, der blev grundlagt tilbage i 62 af Arthur Ellis, og også der er selvfølgelig navnet. Og de holder til i North Yorkshire i England, og er i dag 55 medarbejdere. De har selvfølgelig en hjemmeside, som alle andre, ellispatents.co.uk, og der er der både datablader, applikationer og specs og så videre, alt det man måtte have brug for. Faktisk en rigtig, rigtig god hjemmeside, som de bruger mange kræfter på at vedligeholde og holde opdateret. Så den kan man i hvert fald gå ind og se efterfølgende. Jeg vil egentlig give ordet til dig, Henning, for at fortælle lidt om, hvorfor vi mener, at vi har valgt emnet her i dag.
Jamen tak for det, Peter, og endnu en gang velkommen til jer alle sammen. Til dem, som ikke kender mig, mit navn er Henning Krammer, og som sagt, så har jeg været inden for branchen her i mange år, i over 10 år. Meget inden for banen. Det er jo et spændende område det her, og der sker meget inden for det. Særligt i England, hvor der er en masse spændende projekter, hvor man har meget fokus på mange områder, og en af de fokusområder, man har, det er også med at sætte kabler fast, så man kan sikre dem mod kortslutninger blandt andet. Og det er jo nogle spørgsmål, som vi har arbejdet lidt på, og et spørgsmål, som vi vil stille og belyse her under seminaret, jamen det er sikring af kabler et forsømt område? Er vi opmærksom på de kortslutninger, der frigives ved kortslutninger, når vi sidder og beregner? Hvad ligger der bag udviklingen af professionel kabelbefæstigelse i dag? Hvad er det for nogle standarder, man arbejder efter, hvor der er kommet en masse nye opdateringer? Og ikke mindst kan vi lære af vores kollegaer i England. Og det er jo meget konkret omkring kabelbefæstigelser i dag, men det gælder så også mange andre tekniske områder. Men vi forholder os lige til det emne i dag. Det er sådan under seminaret, så kan man bruge chatten, man kan stille en masse spørgsmål, og efterfølgende kan man selvfølgelig også stille en masse spørgsmål, der vil åbne op, og så kan vi få den dialog. Når vi er færdige med det hele, jamen, i morgen eller overmorgen, så sender vi præsentationen til jer alle sammen, og hvis der skulle være ekstra spørgsmål, så mødes vi gerne. Det var alt for mig. Jeg stiller om til vores kollega Phil, som sidder klar. Hello Phil. Welcome to join us. I'm hereby give you the word for the presentation.
Thank you very much indeed. I hope you can all hear me, and good morning to everybody. We're going to have a presentation here, sort of half an hour or so, 30 minutes, about Ellis and about short circuit testing and about the rail sector. So here we go. I hope everything works, and I hope I come across clearly for you. Okay, so I'm going to just talk about cable fixings, standard specs, the rail sector projects, and sort of and products that we have that are available for use in the rail sector. And first of all, and I hope that everybody doesn't mind me just showing you a picture of what a cable cleat looks like. They're relatively small. They have a large responsibility. They have no moving parts really, and they have no electronics. But and when things work smoothly and they work well, then you don't even notice that they're there. But when things go wrong, cable cleats perform a very important task, and I hope that I can demonstrate that to you this morning. So I'm going to bring all of these little pictures up together, and these are not international definitions. There's no standard that governs what you call these, but these are all types of cable fixings. I've just shown you a cleat, and a cleat is very strong in what we call the radial or the lateral direction. It holds the cables together in position, restrains them. A clamp is also a type of fixing, and a clamp is also very strong in the radial direction, but more importantly, it's very strong in the axial direction. So it actually stops cables from sliding. Particularly in the vertical direction, clamps can be very effective. A strap is really just a cleat that does not attach to any particular structure. So it's floating, holds the cables but floats in the air, if you like, not restrained down to a structure. Hangers, hopefully that's self-explanatory. The cables just lie on the tops of the hangers and sort of adjust from one hanger to the next. They can be cable tied. You can use cable ties to actually attach them, but generally cables tend to be loose laid on the hangers. And a saddle is a very specific piece of equipment, a very sort of high-end fixing, if you like, that's mostly used for distribution and transmission cables at very high voltages. So as I say, these are not absolute definitions. This is just my particular take on the different types of fixings. And with the rail industry, we'll mostly be talking about cleats and hangers. So let's move on to standards, specification and testing. The presentation, as I say, is probably in two halves, so probably about equal amounts of time. So, what is the function of a cable cleat? Why do we need them? I've taken some extracts, 3 sentences here, from what's called the IE triple regs, the wiring regulations, which is a British standard document. And it says here, every conductor or cable shall have the strength and shall be installed to withstand electromagnetic forces that could be caused by any current, and that includes the fault current, short circuit fault current. Cables must be installed to safely hold their own weight, and cables must be installed to protect joints and terminations. So those 3 sentences alone really give you an indication that some sort of cable fixing needs to be used in a cable management system. I hope that makes sense, and hopefully I can demonstrate that to you as we go through. Okay, so this standard here, IEC, the International Electrotechnical Committee, this document, 61914, is the standard that governs the design and the manufacture of cable cleats, cable fixings, if you like. This is the 2015 version, which is the most recent one. And just out of interest, there wasn't a standard for cleats before 2003. So it's actually quite a recent piece of legislation, if you like. So we're still getting used to it. If you're in the business of procuring cleats, then make sure that everything that you procure is actually the 2015 version. That's quite important now, because all cleat manufacturers have had enough time to actually make sure that their standards apply to the 2015 version. Specification. Now, we are a cleat designer and manufacturer, and we supply to the industry. In order to make sure that problems don't occur when these cleats arrive on site, it's very important that people who want cleats specify them in as much detail as they can. I've put up there 3 items which I've called CMS. So these are items that relate to the cable management system, specifically to that document I just mentioned, the standard. We need to know the cable diameter. That sounds obvious, but sometimes we get inquiries when the cable diameter is not certain, or it changes as they go through the project. We would like to know the cable arrangement, whether it's a single cable, whether it's in trefoil formation or a quad, or whether they're bunches of different sizes. That information is very important to specifying the type of cleat. And also the fault level. Fault level is critical, really, for designing a cleating fixing system that's strong enough to hold the cables under short circuit conditions. We can have the RMS fault level or the peak. It doesn't matter which one. Other information that's very useful is the structure. What type of structure are the cleats going to be attached to? Usually it's some form of containment, such as ladder or tray or wire basket. Sometimes it can be directly into a wall, a brickwork or concrete. But having that information is very useful for applying the correct level of fixing bolts, screws, etc., and the material that they're made from. Also, rigid or flexible. Most systems that I've come across are flexible. There will be allowance for some sort of expansion during heavy load periods and contraction when the load reduces. Very, very rare that you'll get a rigid system. So that's everything to do with really the cable and what the cable attaches to, but also the environment. The environment is also very important. Is it going to be a marine environment? Are the cleats going to be exposed to sunlight? Is there a fire hazard? Are they going to be on an offshore structure in a corrosive railway tunnel? So knowing the type of environment is also very, very important for specifying the correct material when you're looking at cleats. If we can get as much information as we can on that sort of slide there, then hopefully that will lead to good specification, the project will run smoothly, and when the cleats arrive on site, they'll be exactly what the project engineers are looking for. Okay, on this slide here, you can see the IEC 61914 standard that I've placed in the middle there, and that relates specifically to the design of that product. However, lots of other things have to be taken into account when designing a cleat. I've briefly mentioned materials and corrosion, UV exposure, fire integrity, and I do realise that all of the numbers there relate to British standards, but there'll be a lot of other international codes and standards that relate into that as well. So it's not just the product design, the metalwork, there's also the environmental issues that you have to take account of. I'm not going to go through each of these in a lot of detail because there's a time constraint, but I'm going to just give you an example of how corrosion and material selection is important, particularly in the rail sector. You can see here I've put down the chemical sort of formula, the chemical pathways for rust. This is iron 2 forming into what's called iron 3 oxide. So everybody's aware what rust looks like, and you will know, or you may have experienced, that on industrial sites such as oil and gas petrochemical refineries, there are hundreds and hundreds of kilometres of cables and cable management systems, cable containment, lots of steel work. A lot of it is galvanised, a lot of it might be stainless, but in certain conditions it will all be prone to the atmosphere and eventually to rusting, to formation of that iron 3 oxide. So, another type of corrosion that you may be familiar with is what we call bimetallic or galvanic corrosion. This is where you have two metals that are dissimilar, and because of their position on what's called the electrochemical series, their level of activity, they can cause corrosion between the metals when they're in the presence of what's called an electrolyte, and generally that just means moisture or water. So the further apart they are on this scale here, the more likelihood there is of corrosion between them in the presence of water. Here we've got brass and we've got aluminium. Aluminium's there, brass is down here, a reasonable gap, so there's likely to be corrosion. Here we've got stainless steel with brass, stainless steel with brass again, or with aluminium, an even bigger gap. So please be aware, with certain metals in contact with each other, corrosion can occur. This is a couple of pictures of railway tunnels. These are both in the UK. This one on the left here is London Underground, and what I'm trying to show you is the hundreds of kilometres of cables and cable fixings that are existing in these tunnels. This one is a project called Crossrail, which runs across central London and is a new project, and you can see here again 5 or 6 tiers of cable management systems. So you might think in a tunnel environment that stainless steel would be a good option because it would last for a long time, it would be good at sort of combating corrosive atmospheres, but you might be mistaken. And my point is, you have to take account of galvanic corrosion in railway tunnels. Train braking systems, you can see on the picture here, when trains apply their brakes, the brake discs and the brake construction is generally made of cast iron or a fairly basic iron material. And when the brake shoes push onto those, you get a lot of iron dust into the atmosphere. Excuse me. And that iron dust will eventually settle onto a stainless steel surface. So if you look where these sit in the electrochemical series, iron, cast iron around here, stainless steel here, there's a fairly big gap, and obviously railway tunnels are prone to moisture and water ingress, and therefore you're going to get accelerated corrosion. So in railway tunnels, try to avoid stainless steel and try to use probably a powder-coated aluminium is probably the best. Powder-coated aluminium with cast iron, a very small gap reduces the exposure to corrosion. Okay, I'm going to talk for 5 minutes or so about short-circuit testing and short-circuit fault levels, etc. This is why cleats come into their own. I said at the outset that cleats weren't very sexy, they don't do very much, but when short circuits arise, this is where the cleat and the strength of the cleat is very, very important. Short circuits occur for lots of reasons. It's usually human error. In most cases, it can be poor installation, it can be weather conditions, but more often than not, it comes down to human error. And I think I've got some pictures of cable faults here. These ones at the top, that one there, where you can see the exploded cable sheath, that's poor installation work. And that was a replication of a fault. And you can see here that these relatively low strength cleats have managed to contain that cable in situ. Even though the cable is very, very badly damaged, it hasn't caused any sort of damage to anything surrounding. This one here on the left at the top is what we call partial discharge failure. So that's a polymer insulated cable that over time, the high potential between the center of the cable and the insulating sheath has caused breakdown of the polymer and therefore an arcing, a flashover over time. That's something that can be managed on a time basis, but in this case it wasn't caught early enough. The two pictures on the bottom here are human error, unfortunately. This one on the right hand side, you can see here there's a flashover between one of the phases and the neutral core on this multi-core cable, and that was down to somebody with a spade digging into the ground in the wrong place, and it's caused a flashover. This one on the left is what we call a catastrophic incident. So this is a three-phase cable, 11 kV, very heavily loaded, and this was a hydraulic digger. The backhoe of a hydraulic machine that went through this caused a very large noise and a big crater in the ground, so a very serious incident. But largely it comes down to human error. I don't want to go too much into electrical theory here. I'm a chemical engineer, so please don't ask me too many difficult questions about electrical mathematics. But what I want you to take from this slide is really this equation at the bottom here, Ft equals 0.17 times IP squared over S. This is a formula that's derived in the IEC, the IEC 61914 standard, and this calculates the level of force that exists in a short circuit condition between conductors. At the top left here you have the simple sort of electromagnetic induction that shows you in adjoining conductors in a magnetic field a force will occur, and you can work out the strength and the direction of that force depending on which way the currents are flowing. What I want you to note here is that you've got the product of two currents, I1 and I2, and you've also got a separation distance here, a distance. So look how that translates, IP squared over a distance. And this diagram on the top right is a sinusoidal AC waveform, but just after a large fault has occurred. Normally it would be flat, like it is here, but in this case there's a very large jump in the peak current. Normally the peak current is √2 times the RMS current value. In this case it's about 70% higher, about 2.1 or 2.2 times RMS. Excuse me. So a much higher IP value, and please note how these relate to this expression here. I've got some video clips that are coming along, and hopefully you'll be able to see how this formula relates to the video clips. So I've got three examples. Excuse me, three examples of three-phase electrical systems. Unfortunately, we can't do this sort of testing in the UK anymore, and we have to travel to the Netherlands, to Germany, to the Czech Republic or the US to carry out these tests. They're very expensive. They can be 10 or 12,000 euros per day, but we're a small company and we've so far carried out over 450, so we have quite a large database of information. I'll explain what you're going to see here. There's a common misnomer, an understanding that stainless steel cable ties are very strong and will perform the job that they're required to do. There is a place for cable ties that are made from stainless, and they can be very heavy duty and they can be very strong, but in some cases where you've got very high fault levels, they won't do the job. What we've got here is a multi-core cable, so that's 3 phases within one sheath. It's on a test bed, and it's held every 300 millimeters with a stainless steel 19 millimeter cable tie. Very strong. This is a typical galvanized steel piece of containment. I think it's ladder. And over the top here you've got some ropes that are holding everything together on the test bed of large slats of wood. This is the generator up here, and this is the buzz bar down here. So a fault is induced at the buzz bar. This bar along the bottom represents 100 milliseconds. So if you bear in mind how quickly that peak current occurs, which is 5 milliseconds, and the current in this case, the fault current is 30 kiloamps RMS, so that relates to about 63 kiloamps as a peak. So I'm going to play this video for you. There's no sound, which I apologize for, because these videos are taken by the test labs and they don't always have sound available. But if you ever get the chance to go to a short circuit test, please do. It's awesome. It's really quite exciting. Let's hope that this works. There, 5 milliseconds. The stainless steel cable ties have been ripped off and that cable is severely damaged. You won't be able to use that one again, I'm afraid. The rest of the video is just lots of bangs, lots of flashes, lots of bright lights, but ultimately that cable has been destroyed. So that was very heavy duty stainless steel ties, and note how quickly it occurred. Okay, let's move on to the second example that I've got for you here. Now this is a very good example of those forces that act between the conductors. Again, this is 3-phase, but their cables are arranged in trefoil. They're not multi-core, they're single cables in a trefoil arrangement. And again, these are spaced with stainless steel cable ties at 225 millimeters or 9 inches. This is a real project that was carried out for a offshore platform in the Gulf of Mexico. So it's an American ladder, 9 inches separation, and the fault current on this one was 118 kiloamps peak. So this is a really good example of those forces. Again, the generator is up here and the buzz bar is down here, and the buzz bar has been concreted into the ground. So let's play this one. It takes probably 30 or 40 milliseconds to get going, but you can see there how much energy is pushed into that containment, into that ladder, and the forces that are acting between the conductors. If you work those forces out in theory, they work out at nearly 6 tons per meter, so a significant level of force. And that was a demonstration to show the client that the specification for steel ties probably wasn't up to the job. So I can show you the solution to that one as we go through. I've got one more example, and this is quite a nice example because it's very familiar sight on the railway industry. What we've got here is 3 phases again, and if you think back to that equation, you can see the separation between the phases is probably 120, 130 millimeters, so it's the biggest separation. The fault level in this particular example is only 40 kiloamps, so it's the lowest fault level and the biggest separation. So looking at the theory of the formula, this should be the least amount of energy. A very typical sort of scene on railways. You see this for hundreds of kilometers in the UK for sure, and you can often see when the train slows down how many times the cable's jumped off the hanger. So this is a hanger rather than a cleat. Please keep your eye on one of these scaffolding type bars at the top here. Let's give this a whirl. Happens very quickly. happened very quickly. I hope you saw that okay, but effectively the top phase here has jumped off the hangers completely, broken the bar, and that could have been something like a signalling control or a points crossing control. So that will have taken a circuit out, and that would have caused a problem on the rail sector. So 3 examples, all 3 phase, showing you how that relates to that formula. I hope that made sense. I'm now going to give you just 2 examples of systems that have been properly engineered, and as you can expect, these are not quite as exciting, but nevertheless worth looking at. So what we've got here is again a trefoil arrangement of cables with cleats, fairly standard medium strength cleats, spaced every 300 millimeters on a wire, stainless steel wire basket. Again, let's give it a play, and you can see here, happens very quickly, 5-10 milliseconds, the forces start to act. So the physics is exactly the same, the forces are there, but the cleats have been specified and designed to hold the cables in position. They are stretched. This is 2 millimeter thick stainless steel, and you can see there's quite a lot of stress being placed on these cleats. They are stretching and yielding, but effectively everything is staying pretty much where it should do. In reality, what you would do if a situation like this has occurred is you would go and inspect the cables afterwards to make sure that there was no damage to the sheaths. With good quality cleats, you'd have a liner in between, so hopefully there would be minimal damage to the cables. But yeah, everybody would be happy with that one. The cables have withheld the short circuit forces, and nothing else has been damaged. I've got one more example of a well-engineered system, and this is the solution to the Gulf of Mexico project. So this is exactly the same test conditions. It's the trefoil arrangement, 118 kiloamps peak, but here we've got fairly high strength cleats, and they're double the spacing. So this is 450 millimeters spacing. And let's play this one and see what happens. And as you might expect, the physics remains the same forces are present, but the cleats are strong enough to hold everything in place. And it all comes down to the level of spacing, the strength of the cleat that you've got, the level of short circuit fault. So there's more than one solution to most of these situations. It's just choosing the right sort of level of equipment for yourself and for your project. And in this case, this was demonstrated to the client, and the client accepted that they had to rewrite the specification. It went out to tender, and we didn't win this project. It went somewhere else, but morally we did the right thing. Some you win, some you lose. Okay, everybody, I'm going to start talking about the rail sector now, and I do admit that I'm going to have a few slides here that are my understanding of the UK rail sector, but hopefully that gives you a perspective of what we're dealing with in the UK. I'm not an expert on the Danish rail sector, which I apologise for, but hopefully as we go through you'll realise the information that I've got is probably similar to a lot of other European countries in terms of investment and renewal of old equipment, etc. So, oops, let's go back one. Rail sector applications. Where can you use cleats and cable fixings in the rail sector? Generally, the rail sector has lower fault levels than most other industries that we deal with. So the applications for using cable fixings are possibly less than they are in the oil and gas or the traditional power transmission market. Where we do use them is generally in the low voltage power distribution, and that can be lots of different areas, in stations, in signalling control, where you've got signalling and communications, but generally anything from sort of 110 volts all the way up to 1000 volts, which is generally classified as low voltage power. And most of the rail motors, most of the rail equipment, and most of the sort of the lighting circuits and things like that tend to operate at low voltage power. It doesn't always require cleats, but it will require fixing. You can't just leave cables to hang or not be fastened down. So it may not be restrained for short circuit purposes, but they certainly need fixing to a structure. In the UK over the last 10-15 years we've seen a lot of electrification work, And where we have the 25 kilovolt AC feeds into the system, there is a requirement for some quite sort of well-designed cable fixing work to be done. So we're seeing quite a lot of that. Limited numbers of cleats, but it's good business anyway. But generally, in the rail industry, low power faults, lots and lots of cables though. But and there's a lot of requirement for fixing because of that. A couple of slides just to talk about the UK rail sector generally. I don't want to dwell on this for too long, but we've seen a huge number of passengers doubling in the last 20 years. Serious amounts of money being put forward into 5-year control periods, £48 billion, 55 billion euros or near to that. A lot of movement into the digital railway to enhance the sort of level of control, the number of trains that can run on a track. Lots of stationary developments. I mentioned electrification. The ambitions have been curtailed slightly because the government has realised how expensive it is. So there may not be quite as much as electrification as we were hoping for. But for the supply chain, lots and lots of jobs and an awful lot of money comes into the supply chain. So it is good business. A couple of what we would call mega projects. You may or may not have heard of these. I mentioned Crossrail, which runs east to west across London. We now have Crossrail 2 that basically runs north and south, 31 billion. High Speed 2 is a bit of a vanity project for the government, 500 kilometres plus, 56 billion pounds, probably 10 years away in reality. But yeah, good exciting stuff. And a level below that, there's a whole, this is just sort of 10 examples that I put there, but there's literally dozens and dozens of key projects, which again can be sort of tens and hundreds of millions of pounds each. And these all tend to be under the auspices of Network Rail. Network Rail is the controlling body, and each of these projects will be implemented by sort of alliances, groups of tier 1 contractors that come together to form an alliance. I'm not going to go through these in a lot of detail, but you Network Rail, if you want to know more information, it's all on their website. Okay. It would be remiss of me not to mention London Underground. In London, we have a very, very large underground system, one of the oldest in the world. And because it's one of the oldest in the world, a lot of it's not in very good state. And they're looking at spending billions of pounds again to bring it up to spec, to make it better, to improve it, to bring more transport, more trains, more rolling stock. And there's various projects. I've just mentioned a few of them there, but yeah, billions and billions of pounds. This map here, by the way, is not the normal map of London. This is a survey that was carried out last year to show the average sort of ambient temperature in some of the lines. That one there where it's red and orange, and this one here, these are the hottest lines as a passenger that you have to struggle through in the summer, and they were over 35 centigrade. And you can see here that those lines, Bakerloo, Central, are being upgraded to make it a better passenger experience. So it's an awful lot of money being spent on the London Underground. So just as an overall summary, if you like, of the UK perspective, the fault levels in the industry are generally low. They are generally less than 20 kiloamps, apart from where we have the feeds into the electrification systems. Getting involved in the UK rail sector is not easy. It's been there for 200 years, and if you weren't there on day one, it's difficult to get involved. We're a small company, and we do find it a struggle to get in front of the right people who make the decisions. And there's a lot of what are called type approvals or certifications. And at the moment, you have to get somebody from within the industry to be your champion or to be your mentor and help you through that process. And it can be very, very difficult. Material selection, very important in the rail sector, usually because they want very long lifetimes, and also because a lot of the areas are quite difficult to work in, particularly in tunnels, quite onerous conditions. And in the rail industry, as it is with a lot of other industries, cable cleats and cable hangers are treated as bulk electrical commodity products. They're not gas turbines, they're not trains, they're not very sexy, and therefore they are low down in the sort of tier level of contracting work. So yeah, commodity products, which makes it difficult to knock on the doors and to get yourself in front of people. But, okay, where are we? Okay, so I'm going to talk a little bit more about the particular products that Ellis have and some of the projects that we've been involved with in the rail sector. I think you'll find this quite interesting, this part. I'm going to start with basic cable hangers. These are very, very basic products. They're manufactured to a BS code, that's 1461, mild steel, hot dip galvanized. I think the galvanizing level gives them a 40-year warranty at the moment, but we can do up to 60-year warranty. Available in 3 different sizes to accommodate cables from down to 10 millimeters up to 100. Very widely used in the industry, a cheap basic product, but we sell a lot of these. A product that's a little bit more advanced, again it's a hanger system, but this is one that we developed about 3 years ago. It's called Pegasus as a brand name, and the difference with this one is it's modular. It's got a modular construction, so you can choose different types of hangers for different sizes of cables. You can put like a bracket on there for smaller control or alarm cables, and you can build it to suit exactly your requirements. It's made of a polymer. It's a glass reinforced nylon, which is very, very strong. It conforms to the London Underground material specification. And running along the back here, which you can't see on this picture, is a marine grade aluminium spine, which gives it enormous strength and again gives it great sort of life expectancy. Very simple fixing into any structures. We can have 1 bracket, or you can have up to 6, or I think we can probably do more than that if required. Similar sort of capacity, up to 100 millimeters diameter for cables. Very, very light. A fraction of the weight of the mild steel hangers that I showed you in the last slide. This is a very light product, therefore much easier to install, and it has a very, very high corrosion resistance. We are quite happy to give 60-year warranties on this equipment. And we are starting to sell it. It's been a bit of a struggle to get there so far, but we are starting to sell it. And also we've seen this product go into other industries as well, mining and quarrying, for example. I've got a few variants to show you on the Pegasus. This is a particular type of Pegasus that we call site fix. So this one is really for where you've got temporary requirements for cable fixings or retrofit applications. It's been used a lot in tunnels and a lot with the London Underground company, and essentially where you've got tunnels that have got very old legacy cables which are not in good condition, that may be rusted or their fixings have corroded away. It's very, very sort of cautious where you have to try and remove these cables from the wall, and you'd rather not do that because sometimes you don't even know what the cables are supplying in cases where we've been involved. So what we can do with the site fix Pegasus is we can actually pull the brackets apart, and we can insert the spine behind the existing cables, attach it to a wall with a certain amount of variation using these wide slots, and therefore we can position the brackets in place to take the weight of the existing cables without touching those cables, and that will take the load and will allow you to do sort of retrofit or to provide a better solution in the future, or these can be used, you know, for many, many years. So it's a way you've got a situation where you've got a delicate system of cables that nobody really wants to get involved with. These will give you a temporary solution. And again, these have been successfully used on the London Underground system. I've got one more variant on Pegasus to show you, which is our profiled curved Pegasus. Obviously this is to be positioned in tunnels, and we can build these to a variety of tunnel diameters ranging from around 2.8 up to about 6 meters. It's exactly the same as the Pegasus, the ordinary Pegasus, but it's just got this curving to it. So everything else is the same. Very high lifetime, very corrosion resistant, very strong, very light, very easy to install. And we're getting involved with London Underground now to talk about implementing these onto some of those big £16 billion projects that I mentioned earlier. I've got a little animation here. I'm hoping that this is going to work. This will just basically show you a little bit more about Pegasus. There's some background music, and hopefully you can hear that too. Okay, thanks very much. I think that went okay. Coming on to another product now that we have. This one is called No Bolts Cleat. It's not the most original name, No Bolts Cleat, but it has no bolts in it. We were quite flattered. Network Rail, the UK operator, came to us and said, could you develop and design a product for us that has no metal parts and requires no tools for installation. This was all due to safety concerns, whereas where contractors had been taking out existing cables, they'd been pulling live cables from studs, and the cables had been sort of scraping across the top of the studs and going through the insulation, and a couple of contractors got quite badly hurt, burned. So they came to us to say, let's develop a new product. It took us 18 months or so. But this product now is fully polymeric. It has no metallic parts. It requires no tools. It complies with IEC 61914. It complies with the London Underground Material Specification, and it's also registered on what's called the PAD system, which is the Network Rail UK national body's very onerous approval system. And it took quite a lot of effort to get through there, but it's got through everything. Very, very high strength, very suitable for harsh environments, very, very easy to install and no tools required, and also cost competitive. I think there's an animation of this coming through soon, but I can show you a picture of where it's actually been used. We've got 2 or 3 projects that this has been used in now. This is one of those stationary developments in London at Waterloo. And you can see here in some of the LV switch rooms and the LV corridors, the cabling corridors, how neat that looks. It looks very, very neat. And the installation contractor was absolutely very, very happy about this. I'm not exactly sure how much time they saved, but it saved them an enormous amount of time. And it's, you know, possibly up to half, probably a 50% saving. And when you're saving time, you're saving money. And installation contractors, that's exactly what they want. So they were very, very pleased to be installing this particular product, and it went very well. So that's a real USP selling point for the No Bolts Cleat. And if I'm allowed to show you another little animation, I can show you one of No Bolts, similar to the last one. Hopefully there's some background music too. Okay. And also, just to say that it did win, the No Bolts Cleat did win a national award, the Electricity Industry Awards 2016. So it's a winner. It's a champion cleat. I've got a couple more to show you, a couple more examples. This is some of the electrification work that I've mentioned going on in the UK network. And this was a very, very harsh environmental condition. It's a tunnel, 7 kilometres, that runs under a marine estuary in the Severn estuary near Bristol. This was being electrified at 25 kilovolts, and the environmental conditions are very harsh. A lot of chlorides, a lot of sulfates, a lot of other nasty chemical environments. And they wanted something that was going to endure those conditions but last for 60 years. So even in this particular case, an ordinary stainless steel wouldn't have worked. Aluminium, even powder-coated aluminium, was deemed to be a risk. So we've gone for fixing brackets that are made with super duplex, so very, very high chromium content with a traditional 2F clamp. So 3,500 of these in the Severn Estuary Tunnel, and we were very happy to give a 60-year warranty on those. And I think this is the last one that I've got you as an example of Ellis products in rail projects. This is the Alpha product, an aluminium trefoil cleat. This is HS1, so high-speed 1 Eurotunnel. This is the approach from London to the tunnel entrance in Kent, in Dover, Ashford. And 250,000 Alphas have been installed on Eurotunnel. They were aluminium and they were powder coated. I mentioned beforehand the issues of brake dust, etc. So 250,000 Alphas in the Eurotunnel. And also, if I go up one, getting a bit confused here. We know of other products that are also used in the rail sector. As a lot of our products go through distribution through companies such as yourselves, sometimes we don't always know exactly where they've gone. But on the UK system, if you know where to look and take a picture, I can find you these products on the UK rail system also. And just to give you a slide here at the end of my presentation, which shows you that we operate across all industrial sectors, not just the rail, but we do oil and gas, we do power, we do infrastructure, data centres, chemicals refineries, and I would like to think that we have a cable fixing solution for just about any industrial sector that you come across. So I think I'm just about to go on to my last slide, which hopefully says thank you, and thank you for listening to me. I hope it came across okay at your end, and please ask any questions directly or through my colleagues at Wexøe there, who will be happy to give you my contact details if necessary. Thank you very much indeed.
Thank you very much, Phil. It was a very interesting presentation. Especially the videos that you have made give a very good impression about the force you have in the power when you have short circuits. We have got some questions, and one of the questions was if we will send the presentation. We will send the presentation latest tomorrow. So, and if there should be further question, of course, we are welcome. You are welcome to call us, send us a mail, and then we will come for a meeting. Phil, I will change back to Danish. I hope this is okay for the last one.
No problem at all.
Igen, tak for alle deltagerne. Jeg ved, mange af jer kender til os, men her er lidt omkring os, der har med det at gøre inden for stærkstrøm. Mange ansigterne kan I måske kende fra jeres dagligdag, men igen, endelig tage fat i os, hvis der er noget.
Ja, men jeg har heller ikke så meget mere at sige. Hvis ikke der er flere spørgsmål, skal vi lige se, om der kommer noget. Men ellers, som sagt, ja, vi sender præsentationen og også den her gennemgang fra Phil med hans kommentarer. Så den kommer der et link til inden for ganske kort tid. Så hvis ikke der er flere spørgsmål, så slutter vi herfra og siger tak for jeres tid. Vi løb desværre lige 10 minutter over. Det må vi gøre bedre næste gang. Men tak for jeres deltagelse, og have en fortsat god dag. Ja. Hej.